Imagine this, a tiny white ball just zipping back and forth across the table, like impossibly fast, spinning like crazy. It demands these split-second reactions, pinpoint precision, and this constantly adapting strategy.
Yeah, the whole intense athletic dance of a table tennis rally.
It seems simple enough, right? You just hit the ball back. But for a machine, getting good at this, that's
Yeah.
one of the toughest challenges in robotics.
That's exactly right. Table tennis sits in this really unique sweet spot for robotics research. It's not the slow, careful work you see in like car assembly.
Right.
And it's not the huge challenge of making a robot walk upright on two legs, which is more about dynamic balance and locomotion. This is different.
It's incredibly rapid, demands ultra-high precision, and needs continuous interaction with something that's always changing the ball, and often a human opponent, too.
Exactly. And that's why we're here on the deep dive today. We're going to tackle this really fascinating challenge right at the intersection of sports and, well, cutting-edge robotics,
Yeah.
building a robot that can play table tennis.
We've taken a deep dive into a whole stack of source material that one of you, our listeners, sent over. It covers pretty much the entire history and evolution of robotic table tennis research.
Yeah, we're talking everything from the very first attempts decades ago all the way up to the really sophisticated AI-powered systems being developed right now.
So our mission today is basically to unpack this incredible journey for you. We want to highlight the key technological breakthroughs, the things that made progress possible.
And also shine a light on the challenges that still persist, and maybe talk a bit about what this all means for the future of robotics itself.
Yeah, we're going to pull out the essential insights, just so you can get up to speed quickly on this really dynamic field.
And I think it's really worth taking just a second to understand why this specific sport, table tennis, became such a compelling benchmark for robotics researchers all over the world.
Right. It wasn't just random. There are reasons.
Yeah, I mean, first off, it demands incredibly rapid perception. You've got milliseconds, literally milliseconds, to see and track that tiny, fast-moving ball.
And then you need that high-speed, precise motor control to get the robot arm and the paddle exactly where they need to be, like right now.
Uh-huh. And on top of that, there's strategic thinking. You can't just, blindly whack it back. You need to decide how and where to return it to actually challenge your opponent.
And you have to constantly adapt to whatever the other player is doing. Their spin, their placement, their speed.
Exactly. And the core problem here, intercepting small, fast objects with high precision in this dynamic environment, that skill, that capability, it's needed way beyond the ping pong table.
Oh, yeah, absolutely. You can think about industrial robots needing to catch parts on an assembly line, maybe?
Or even potential applications in things like search and rescue or other really agile manipulation tasks. So getting this right, succeeding here, it has really wide-ranging implications for robotics as a whole.
Okay, so let's dive in. Let's unpack this journey, maybe starting right at the beginning, the genesis, the really early days, when just getting a robot to even touch the ball probably felt like science fiction.
Definitely. And the desire, the aspiration to automate table tennis, it goes back surprisingly far. Well before sophisticated robots were, common at all. That period from the 1970s through the early 1990s, that really laid the groundwork.
And the first things we saw, they weren't necessarily trying to beat a human champion, were they? More like tireless practice partners.
Precisely. Think about early commercial efforts like Joe Newgarden's work. That led to the Nuji Robopong. He actually started on this as a hobby way back in 1972.
Wow, 72.
Yeah, but it didn't actually see its first commercial release until 1988. And these early machines, they were designed primarily as reliable ball launchers. The focus was on consistent mechanics, feeding balls at different frequencies, different placements.
And that basic concept evolved over time, didn't it?
Yeah.
You see later companies like PowerPong, founded much later, 2012, I think, they started adding more features.
Right, things like variable spin, programmable drills, maybe ball recycling systems. They weren't smart in the AI sense we think of today, but they were important. They showed what automated interaction could look like.
And they gave researchers a tool, right? Something to test their own systems against.
Exactly. They established a baseline for reliable ball delivery. But the real spark for academic research, especially research aiming towards competitive play, that really came from Professor John Billingsley at Portsmouth Polytechnic in the UK. He started organizing robot table tennis competitions way back in 1983.
That sounds like a brilliant way to catalyze research. You give different university teams the same challenging problem, let them compete, measure their progress.
It absolutely was. But, and this is crucial, These early competitions, they don't use the standard rules of table tennis. Billingsley knew the technology back then, the vision systems, the processing power, the control. It just wasn't up to the full task yet. So they used modified rules to make it actually achievable.
Modified rules,
Yeah.
like a smaller table or something, or maybe a higher net.
Yes, both of those were part of it. And critically, they added these wireframes, like physical guides, positioned over the table and the net. The ball had to pass through these wireframes.
Okay.
And they also limited the ball speed, kept it under 10 meters per second. All of this drastically constrained the ball's possible trajectories, made it much easier to predict.
I see. Yeah, trying to track and predict a wildly spinning ball coming at you at like full speed with 1980s camera tech and computer chips. And that sounds, well, basically impossible. The wireframes simplified the problem space.
Exactly right. They were a really pragmatic response to the severe limits of 1980s tech. But even with those constraints, these competitions really catalyzed a lot of early foundational research in the field.
And out of this era, this constrained environment, came a system that everyone points to as a real landmark achievement.
Yes, that would be Russell L. Anderson at AT&T Bell Labs in the late 1980s. His system is widely celebrated as the first robot capable of playing table tennis against actual human opponents.
Whoa, against humans. Even with the codified rules, that's a massive leap from just launching balls, isn't it? What did his system actually look like?
Well, he used a PMA 260 industrial arm, probably mounted on the ceiling, maybe with a stick extension to give it more reach. But the real marvel, the thing that people called a tour de force, was his vision system. He developed a real-time 3D vision system that reportedly used 4 60-hertz cameras.
4 60-hertz cameras.
Yeah.
Okay, that's standard video frame rate back then. But how on earth did he process all that video data fast enough in the late 80s to actually react to a moving ball?
That's precisely where his custom hardware came in. He designed specific hardware cards, VME cards, things like Tri-X, which could process video streams incredibly quickly for the time, and GIFE, a custom processor board built specifically for the rapid 3D calculations needed to track the ball's position in real time.
So custom chips just for this task.
Exactly. It really highlights the hardware focus of that era. If you needed speed, you often had to build specialized hardware because general-purpose computers just weren't powerful enough yet.
Okay, so custom super fast vision hardware. What about the robot's brain? How did it decide where to move the paddle?
The control system was based on an expert system. You can think of it like a sophisticated set of if-then rules. If the ball is detected in this position and it's moving with this velocity, then calculate where the paddle needs to intercept it. It made decisions based on the ball's current state, prioritizing robustness and continuously integrating new data as it came in from the vision system.
And how well did it actually play?
It could reportedly rally for approximately 20 consecutive hits against a human opponent, which, again, for the time, was remarkable.
A tour de force in experimental robotics, a landmark work. Yet those are high praises, especially considering the tech available. And this wasn't just happening at AT&T Bell Labs, right? There were other pioneers.
No, absolutely. Pioneering efforts were happening globally. Over in Japan, you had researchers like Hashimoto at the University of Tokyo developing systems with highly dynamic arms, using different kinds of vision systems like linear sensors for fast position measurement.
Okay.
Others, like Miyazaki, Matsushima, and Nakashima, were doing really systematic studies of ball dynamics, figuring out how spin affects the flight path. That's the Magnus effect.
Yeah.
They were developing prediction models like LWR, locally weighted regression, which is an early machine learning technique to learn input-output maps.
Learning from data, even back then.
Yeah, and refining control techniques too, like ILC, iterative learning control, which helps a system improve its performance over repeated trials of the same task.
And what about in Europe, beyond Billingsley's initial competitions?
Well, ETH Zurich, the Swiss Federal Institute of Technology, led by Fessler and colleagues, they actually won the last Billingsley competition in 1993. They had a 60OF system, and notably, they used a parallel distributed computer network to get the processing power they needed. Another example of creative workarounds for limited computation.
So if we look back at that whole early era, say up to the early 90s, what were the absolute biggest roadblocks they were hitting?
Definitely vision systems, low resolution, slow frame rates, sensitivity to lighting conditions, just reliably seeing and tracking that small, fast white ball was a huge challenge.
Right.
And that was compounded by limited computational power. Running anything complex in real time was just incredibly difficult on standard hardware. You needed custom stuff like Anderson built.
And actually getting the robot arm, often these big industrial arms, to move fast enough and precisely enough.
Exactly. Control algorithms were pretty basic compared to what we have today. Achieving both high speed and high precision simultaneously with the available robot arms was really tough. And plus, there was the fundamental challenge of accurately understanding ball dynamics, especially the tricky effects of spin, the Magnus force, and also how the ball bounces off the paddle and the table. It's surprisingly complex physics.
It really does put into perspective the sheer ingenuity required back then, just making a robot play at all.
Yeah.
It was remarkable. It wasn't about some super smart AI figuring things out.
No, not at all. It was often about clever mechanical design, building custom hardware sensors or processors, or finding smart ways to simplify the problem, like those wireframes. The focus was very much on the hardware side because the algorithms just couldn't compensate for those limitations yet.
So the Billingsley competitions ended around 93, not because the problem was solved, but maybe because they'd hit the limits of what was possible with that era's technology within that specific constrained framework.
That's a good way to put it. You really needed some fundamental technological advancements across the board in computing, in sensors, in algorithms, before you could realistically tackle the full complexity of the game without those constraints.
Which brings us nicely to how technology did evolve over the next couple of decades. This is where things start to accelerate, right?
Oh yeah, this is where things get really interesting. The journey since those early days, it's a story of these dramatic leaps forward, but across several interconnected areas. It wasn't just one single breakthrough.
It was more like progress in vision allowed progress in prediction, which allowed better control, that kind of thing.
Exactly. Breakthroughs in vision systems, trajectory prediction, the robot hardware itself, and the control strategies, they all fed into each other. It was like a complex system learning and improving together.
Okay, let's break that down. Let's start with seeing the ball, the vision systems. Where did we go from those 60 hertz cameras and shadow tricks?
Huge progress there. We went from relying on those early techniques, or basic blob detection with low-res 60 hertz cameras, to eventually modern high-speed multi-camera systems. The mid-era saw higher frame rates appearing, maybe getting up to 100, 150 hertz, using more reliable, let's say, traditional computer vision techniques.
But the real game changer more recently has surely been deep learning, hasn't it? Using neural networks.
Absolutely. Applying convolutional neural networks, CNNs, things like ULF5 are often mentioned, means you get incredibly robust ball detection. Even if the background is cluttered or the lighting isn't perfect, studies report things like 98% accuracy just for detecting the ball.
Wow.
But maybe even more critically, deep learning is starting to enable accurate spin classification. By analyzing the subtle visual appearance of the ball, maybe the blur of the logo, or even tiny deviations in its early trajectory, these systems can start to estimate how the ball is spinning.
Which is crucial for predicting where it's going to go, especially after the bounce.
Precisely. And some research is even looking at cutting-edge stuff like event cameras, which work very differently, only reporting pixels that change, offering potentially extremely low latency sensing.
So better vision means you can feed better data into the next step, predicting the ball's path more accurately. Tell us about trajectory prediction. How did that evolve?
This also evolved significantly. Early on, like we said, it was basic physics, maybe just gravity and simple air resistance, if that. Then came more detailed physics models that explicitly tried to account for the Magnus effect from spin, and also more sophisticated models of how the ball bounces off the paddle and table surfaces. Nakashima's work was key here early on.
But physics models, they aren't always perfect, are they? Especially with all the variables in the real world.
Exactly right. They can be brittle. So data-driven approaches started to emerge alongside them. We mentioned early machine learning, like LWR learning, input-output maps directly from observing ball flights, and then standard neural networks, NNs, came into play.
And now, in the modern era, what are the cutting-edge prediction techniques?
Now we see more advanced neural network architectures being used. Things like LSTMs, long short-term memory networks, which are really good at understanding sequences over time, perfect for predicting a trajectory. Or specialized architectures like cascade NNs, sometimes designed specifically to tackle the challenge of accurately predicting the path of spinning balls.
And it sounds like often the most powerful modern approaches kind of combine the best of both worlds, physics and learning.
Often, yes. We're seeing a lot of hybrid physics plus learning models. The physics model provides the underlying structure and constraints, which is really valuable, and then machine learning refines that model using real-world data to make it incredibly accurate, capturing effects the pure physics model might miss.
Okay.
And the MIT system we'll talk more about later uses a different but very powerful approach based on formulating the prediction as an optimal control problem, OCP. It's deeply rooted in mathematical physics and control theory, but they optimize it computationally for speed and accuracy.
And the result of all this advancement?
The result is much more accurate forecasting of the ball's entire path, including where it will land, how it will bounce, and exactly what state it will be in its position, velocity, spin, at the precise moment the robot needs to hit it, especially crucial for those tricky spinning shots.
Okay, so you can see the ball much better. You can predict where it's going with much greater accuracy. Now you need the physical ability, the robotic arm hardware, that can actually get the paddle there fast enough and hit it effectively.
Right, the robot's body. This has also gone through a huge transformation, from adapting those relatively slow, heavy industrial arms like the PUMA 260, or using simpler custom kinematics like robots built with linear axes moving along rails, to much more capable dynamic machines. In the mid-era, there was exploration of more anthropomorphic arms with joints lay out more like a human arm, giving them more dexterity, and even some early humanoid robots attempting the task.
And today, what's the focus for the hardware now?
Today, the focus is really on extreme dynamism and athleticism. Modern arms developed specifically for this task are often lightweight, built with materials that reduce inertia, have high torque motors for rapid acceleration, and overall low inertia design.
Like the MIT arm.
Exactly. The custom 5DOF arm on the recent MIT robot is a prime example. It was designed from the ground up for extremely high acceleration and speed right at the paddle tip. We also see advanced industrial arms, like the standard ABB arm used by Google DeepMind, but often mounted on linear gantries extra rails that let the whole arm move side to side or forward and back.
So that effectively adds more degrees of freedom, DOF. Gives it a much larger, more flexible workspace to cover the table.
Precisely. The Google system is listed as 8 DOF. The goal now is really achieving or even exceeding human-level speed and power in the actual strike.
And all this better hardware, better vision, better prediction, it all has to be orchestrated by the control strategies. How the robot actually decides how to move and how to hit the ball in real time.
Yes, the brain of the operation coordinating everything. Early on, as we mentioned, it was mostly reactive. Rule-based expert systems like Anderson's or simple input-output maps learned from limited data using techniques like LWR or ILC.
Then in the middle period.
The mid-era saw a lot of exploration of imitation learning. This is where robots learned striking motions by observing human demonstrations. Researchers would record a skilled player hitting the ball and then use frameworks like DMPs, dynamic motor primitives, or MoMP movement primitives, pioneered by folks like Mueling, Kober, and Peters, to encode and reproduce those movements on the robot.
So basically learning by copying human experts.
Kind of, yeah. Learning the how of the movement. But the modern era has really shifted towards more proactive and adaptive control strategies that can generate novel movements too.
Like model predictive control.
Exactly. Model predictive control, MPC, which is used by the MIT team, allows the robot to constantly replan its movement trajectory over a short time horizon into the future based on the very latest prediction of the ball's path. It's effectively thinking a step ahead and reacting in real time to any changes or prediction updates.
And the other big one is reinforcement learning, right?
Yeah.
Especially from DeepMind.
Yes, reinforcement learning, RL, where robots learn complex strategies and skills through massive trial and error, typically in simulation. They get rewarded for successful hits and penalized for misses. And over millions of trials, they figure out what works.
And they often use a hierarchical approach for RL, don't they? Like a manager deciding the strategy and a worker executing the skill.
Precisely. You might have a high-level controller, HLC, that looks at the situation and decides, okay, I should play a forehand drive to the opponent's backhand corner. Then it calls a specific low-level controller, LLC, that has learned through RL how to execute that specific forehand drive motion accurately and powerfully.
So this shift from just reacting or copying to MPC and RL, it allows robots not just to intercept the ball, but to actually plan varied strokes, maybe apply different spins, and adapt in real time to what's happening in the rally.
Exactly. It moves towards more intelligent, flexible, and strategic play.
So looking across all these interconnected areas, vision, prediction, hardware, control penning, you really see this clear thread emerging. Learning approaches, especially deep learning and reinforcement learning, they've become absolutely central, haven't they?
Absolutely. It's a huge shift. From minimal learning in the early days, maybe just calibrating parameters, to machine learning and particularly deep learning and RL becoming integral to pretty much every subsystem today. You have CNNs for seeing the ball, maybe LSTMs for predicting its path, and RL for learning complex hitting strategies and the underlying motor control.
But the overall progress, it isn't just about one breakthrough in isolation, is it? It's the synergy.
No, that's absolutely crucial to understand. The progress we've seen is really a systems-level achievement. Better vision gives you more accurate data, which feeds better prediction models. Those better predictions enable more sophisticated control strategies like MPC or RL to actually work effectively. And those advanced control strategies can then fully utilize the capabilities of the new advanced high-speed hardware. They all build on each other.
A bottleneck in one area holds everything else back.
Pretty much, yeah. You could have the fastest arm in the world, but if your vision system is slow or your prediction is wrong, it doesn't matter.
And a really critical tool that makes training these incredibly complex high-speed systems possible today, especially for the RL approaches, is simulation.
Oh, simulation is absolutely vital now. Trying to train these dynamic actions, especially through RL, which might require millions or even billions of trials purely on a real physical robot, it would be incredibly slow, super expensive, and you'd constantly risk damaging the hardware with mistakes or collisions.
So the goal now is often this sim-to-real transfer. Train it entirely in the computer world and then have it just work on the real robot.
That's the holy grail, yes. Zero-shot sim-to-real transfer. You train the robot's control policy entirely within a high-fidelity simulator, and ideally, it works correctly on the real physical robot the first time without needing any further real-world training or fine-tuning.
That must require a really good simulator then, right? It has to be incredibly realistic.
It really does. The simulator has to accurately model not just the basic physics, like how the ball bounces and spins, but also all the real-world complexities. Things like sensor latency, the delay in getting information, sensor noise imperfections in the readings, motor limitations the robot can't instantly achieve any speed or torque, even subtle things like the statistical distribution of how real balls actually behave.
And for the massive scale of training needed for RL.
Right. You also need things like automated environment resets. Imagine in simulation, after every hit or miss, you need a system that can instantly collect the virtual ball and put it back into play for the next trial. You can't have a virtual person resetting it each time. Google DeepMind, for instance, used an evolutionary strategy called BGS, Bayesian Guided Search, within their simulation environment to efficiently explore the huge space of possible control policies and find good ones quickly.
So you're simulating not just the physics of the game, but the entire physical setup, including all its imperfections, and even automating the training process itself within the simulation.
Precisely. Getting sim-to-real to work reliably, especially for such dynamic tasks, is a major research focus in robotics right now, pushing the boundaries of how well we can model reality in software.
It's fascinating when you think about how these same technological advancements, better perception, predicting complex dynamics, agile control, successful sim-to-real, how they're impacting fields so far beyond the ping-pong table. Like autonomous vehicles needing to predict pedestrian movement, or advanced manufacturing robots handling delicate parts, or even surgical robots needing precise control.
It absolutely is. Table tennis provides this wonderfully challenging, yet contained and visually rich environment to really push and refine these core robotic capabilities that are needed across countless applications. It's a fantastic, demanding test bed.
Which brings us neatly to the modern era, looking at the state-of-the-art systems that are really pushing the envelope today, showing us what's possible right now.
Right, and maybe two of the most prominent recent examples kind of showcase slightly different philosophies and approaches to tackling this challenge.
Okay, let's start with the Google DeepMind system. Their focus seems very much on competitive play against humans, using that powerful AI approach.
Yeah, DeepMind's stated goal seems squarely focused on creating a robot that can genuinely compete and, ideally, win against skilled human players. Their setup, as we mentioned, uses a standard ABB industrial arm, but it's mounted on linear gantries. This gives the whole system 8 DOF, degrees of freedom, meaning it has really wide coverage and flexibility across the table area.
And their core approach, as we touched on, is heavily based on that reinforcement learning trained in simulation.
Yes. They train their control policies extensively in simulation, using that BGS evolutionary strategy we mentioned earlier. They employ that hierarchical policy structure, the high-level controllers for strategy, like choosing which stroke to play, and the low-level controllers for executing the precise movements for those strokes.
And a key technical achievement for them was getting that complex policy learned in simulation to work directly on the physical robot.
Exactly. Their reported ability to achieve zero-shot sim-to-real transfer for such a complex dynamic task is really significant.
So how does it actually perform against humans? That's kind of the bottom line for a competitive system, isn't it?
It performs impressively well, especially considering it learned purely in simulation. In matches against unseen human players, whose skill ranged from beginner level up to tournament level, their robot won 45% of the matches overall.
Almost half.
Yeah. Drilling down, it had a 100% win rate against the beginners, and it won 55% of the matches against the intermediate players. In cooperative rallies, where the goal is just to keep the ball going back and forth, they've shown it can achieve 340 consecutive hits.
Wow. Winning nearly half the time against intermediate players and never missing against a beginner.
Yeah.
That's pretty remarkable for an AI learning essentially from scratch in a simulator.
It's a really powerful demonstration of the potential of reinforcement learning, coupled with high-fidelity simulation and effective sim-to-real transfer for achieving high levels of competitive performance in a really dynamic physical task.
Okay, now let's switch gears and look at MIT's recent breakthrough. Their paper just came out, submitted May 2025, I believe. They seem to be focused on a slightly different aspect.
Yeah.
Achieving extreme high-speed precision and raw physical athleticism.
Yes. The MIT team with key researchers like David Nguyen, Kendrick Concio, and Professor Sang-Ba Kim, they definitely took a different route. Their emphasis is much more on optimizing the physical hardware performance and using advanced real-time control theory. Their setup features a custom-designed, lightweight, high-torque 5DOF arm.
So built from scratch just for this.
Exactly. It's fixed to the table for now, though they do mention plans for integrating mobility in the future, and they use high-speed motion capture cameras for tracking the ball, which gives very accurate position data.
So, custom hardware, specifically engineered for speed and agility, not just adapting an existing industrial arm. And their control approach, it's not primarily AI trained on winning matches, but more grounded in physics and mathematical optimization.
That's correct. Their control strategy is deeply rooted in physics-based prediction combined with an optimal control problem, OCP framework. You can think of OCP as mathematically finding the single best way to achieve a specific well-defined goal, like hitting the ball with a certain target speed, spin, and placement. They use this OCP framework to calculate, in real time, the ideal state for the paddle, its exact position, velocity, and orientation needed to execute specific, predefined stroke types, like a topspin loop, a flat drive, or a backspin shot.
And they embed this optimized move calculation within that model predictive control system we talked about.
Precisely. The MPC framework acts as the outer loop. It takes the latest ball prediction, decides which type of stroke is appropriate, runs the OCP calculation to figure out the optimal paddle state for that stroke, and then computes the robot arm trajectory to achieve that state, constantly replanning over a short time horizon based on new incoming ball data. This allows for extremely rapid real-time reactions.
And they needed serious computing power for this.
Yeah, to achieve the necessary speed for all these calculations, vision processing, state estimation, OCP solving, MPC planning, sending commands to the arm they actually use, 3 computers operating in parallel, sharing the workload.
So how does this focus on optimized hardware and advanced control translate into actual performance? What are their results?
Well, they recorded a high hit rate in their tests, around 88% across those different spin types when hitting 150 consecutive balls. But the most eye-catching result, the one that really makes you sit up and take notice, is the paddle strike speed. They reported achieving paddle speeds up to 19 meters per second.
Whoa, 19 meters per second. That sounds really fast for a robot. How does that compare?
It's significantly faster than what's been reported for most other research systems.
Yeah.
And it's genuinely starting to approach the kinds of speeds that human elite players generate on their returns, which might be in the, say, 21 to 25 meters per second range.
So this is a major step towards achieving real human-level athleticism and power in a robot.
It really seems to be. It's a powerful demonstration of what can be achieved through tightly integrating optimized hardware design with sophisticated physics-based real-time control theory. And their system isn't just hitting hard. They also showed it can aim returns to specific target locations on the opponent's side of the table, adding that strategic element of placement.
So you have these two really interesting cutting-edge examples. Google DeepMind pushing the boundaries of AI in simulation for competitive strategic play, and MIT pushing the limits of high-speed physical execution and precision using advanced control and custom hardware. Two distinct, but maybe complementary paths towards a highly capable robot.
They really highlight the different facets of this complex challenge, yeah. And they show what's possible with different engineering philosophies and focuses. And of course, it's not just these two prominent examples making progress.
Right, you mentioned Omron in Japan earlier.
Yeah, Omron's Morpheus robot, which often appears at tech shows. It takes a different approach altogether, really focusing on human-machine harmony and tutoring. Its goal isn't necessarily to beat the human, but rather to adapt its play to keep rallies going, maybe analyze the human's technique, and actively help them improve.
That's a fascinating goal in itself. Robotics for collaboration and teaching, not just competition.
Exactly. And you continue to see major research hubs in places like China. There are systems from BITI, Beijing Institute of Technology, that have demonstrated robot versus robot rallies. You have ISUN developing incredibly fast prediction systems, and recent work from Zhejiang University and others applying AI for things like coaching analysis or generating more human-like movements for the robots.
And Germany's still active too.
Oh yes, groups like TU Darmstadt and the University of Tübingen have a long history here and continue to do important work, often focusing on areas like imitation learning, improving spin detection, and applying reinforcement learning for optimizing specific aspects of stroke execution, sometimes using standard industrial arms like KUKs, which helps make their findings potentially more accessible to others.
So the field is truly global, with this whole network of researchers and institutions contributing from different angles. It feels like we've moved from mostly academic labs grappling with the fundamentals.
Right, grappling with basic sensing and control problems.
To now having significant, really resource-intensive efforts happening in major corporate labs like Google DeepMind and Omron, alongside specialized academic groups pushing the state-of-the-art in specific areas like MIT with high-speed control.
Yeah, the landscape has definitely evolved.
And seeing these different modern approaches, Google's AI competitor, MIT's high-speed athlete, Omron's collaborative tutor, it really underscores how multifaceted that goal of reaching human level in robotics actually is. It's clearly not just about one single capability.
It definitely highlights that human level is a really complex benchmark, and it's being tackled from all these different angles simultaneously: strategy, athleticism, interaction, robustness, maybe even coaching ability.
Which leads us naturally to thinking about the road ahead. We've seen this incredible progress, right? From those rudimentary machines struggling just to make contact to robots now capable of really dynamic, complex, high-speed play. But where do we go from here? What are the big hurdles that still remain?
Well, we've certainly seen those paradigm shifts towards learning, towards unconstrained environments, towards high speed. But yeah, challenges definitely remain. Spin, for instance, even with the progress in deep learning for classification, it still seems like a major sticking point.
Right. Consistently dealing with really heavy or tricky spins.
It is. Being able to robustly perceive all types of complex spin accurately, like heavy side spin combined with top spin, then predicting its exact effect on the trajectory and the bounce, especially off different surfaces, and then strategically generating a wide range of effective spins in return, doing all of that reliably at elite human speeds, that's still incredibly tough.
And what about the strategy side? Can these robots really understand the game, anticipate opponent weaknesses, adapt mid-match?
That's another huge area. Moving beyond, let's say, learned tactical responses or programmed patterns to true deep game understanding. Things like long-term strategic planning across multiple points or even games, or sophisticated real-time adaptation, not just to the ball, but to an individual opponent's unique style, their habits, their tells, maybe their fatigue levels. That level of cognitive game intelligence is a significant, still largely open challenge for robot AI.
Okay, what about the physical robot itself? These high-performance systems like the MIT one or the DeepMind setup, they sound pretty complex and probably very expensive.
They absolutely are. Right now, most of these top-tier systems are expensive laboratory prototypes. Achieving the necessary cost-effectiveness and robustness for widespread use outside controlled research environments is a major hurdle. Can you build one that's affordable enough for, say, a table tennis club, and can it withstand the inevitable missed shots, paddle collisions, or just the general wear and tear of regular use in a less controlled setting?
And most of them are still fixed in one spot, right?
Yeah.
They don't have the footwork.
Exactly. Most current high-performance systems lack the full mobility and whole-body coordination of a human player who needs to move rapidly around the court to cover the entire table. Researchers are definitely starting to work on integrating legs or mobile bases, but coordinating that movement with the high-speed arm action adds another layer of complexity.
So making them cheaper, tougher, and able to move around the table like a person. Those seem like key practical steps.
Definitely. And related to the cost is just making these advanced systems more accessible in general, making them affordable enough to be used widely, perhaps as advanced training partners for players and coaches outside of elite research labs. That's another key future goal for the field.
But as we've kind of touched on throughout this deep dive, it isn't just about table tennis, is it? The implications are broader.
Not at all. The solutions being developed for these challenges, things like robust perception of fast-moving objects, predicting complex physical dynamics, agile control of high degree of freedom arms, achieving reliable sim-to-real transfer, learning complex strategies in dynamic environments. These are fundamental capabilities needed to advance robotics across countless fields.
Right, from manufacturing and
But
logistics.
healthcare, planetary exploration, maybe even better assistive robots in our homes. Table tennis just happens to serve as this incredibly demanding yet conveniently contained environment to really push the limits and refine these core robotic technologies. It really is a microcosm of robotics progress.
It really is kind of the unfolding game of robotics itself, just played out on a 9 by 5 foot table.
Yeah.
And it raises a final, maybe provocative thought for our listeners to consider. As these robots get better and better, as they approach or maybe even surpass human capabilities in certain aspects like speed, precision, or prediction, well, they simply end up trying to imitate human play, mimicking our strokes, our serves, our familiar strategies.
Or is there another possibility? Will they invent a completely, well, alien style of table tennis? A style that's optimized not for human biomechanics, our reaction times, our muscle limits, but for their unique mechanical advantages.
What would that even look like?
Maybe something like absolute inhuman consistency on every single shot, regardless of pressure. Or maybe exploiting their ability to make tiny, incredibly fast micro adjustments that a human couldn't perceive, let alone replicate. Or perhaps leveraging perfect mathematical prediction of complex trajectories, completely immune to fatigue or psychological factors. Could they potentially uncover tactics, movement patterns, ways of playing the game that we humans, constrained by our own biology, could never have even conceived of?
That's something to mull over. Could a robot player, through pure optimization, end up showing us a completely new way to play this game we thought we knew so well? The possibility is certainly intriguing. The journey clearly continues.